The droop controller and the virtual synchronous generator controller Professor Humberto just presented are both, they have both the roots from the conventional electrical power systems with synchronous generators. However, there is another promising technology that have been proposed recently. The virtual oscillator control is one of them. It follows an analogous path, but the idea here is not to mimic in some way the behavior of electric power systems, but to mimic the behavior of oscillators. In the particular case of the VOC, the virtual oscillator control, it has the aim to mimic, to emulate a weakly nonlinear limit cycle oscillator. As some properties, good properties, some attributes of this controller, it has the ability of asymptotic synchronization among the parallel connected voltage source converters. Besides, it's possible to share power among the converters. And this is a very interesting feature because the power share is achieved even without measuring the powers. So that, especially for single-phase systems, this is very interesting because there's no need to use modifications for calculus of powers in single-phase systems like SOGI, second-order integrators, Hilbert transform, or other even more complex transformations. There's other attributes that, despite the virtual oscillator control doesn't having its roots from the power system, it's still possible to assign a droop behavior in steady state. So virtual oscillator-based controllers have a transient response that corresponds to a behavior of oscillators, and in steady state you can assign a droop behavior to them. This is a very interesting feature. However, there are some shortcomings. First, the application to three-phase systems is not straightforward. Okay, and focusing on its original proposal, the VOC is not dispatchable, which means that it's not possible to assign active and reactive power set points to it. So it's not dispatchable in its original formulation. Also, it implements a nonlinear oscillator, so there are some linears of low order present on the voltage to be synthesized by the converter. However, it's worth mentioning that both of these shortcomings have been removed or mitigated, or I can say that you are get rid of these limitations in the paper that was published in the beginning of this year, the paper of Wall et al. Okay, but we are not focused on these details. Okay, we are going to continue and focus on the other dispatchable virtual oscillator that we will see in the second, after the VOC. Okay, the VOC is based on the implementation of the Van der Pol oscillator. The Van der Pol oscillator is drawn in this figure. Here we have a LC tank. The LC tank, it defines the frequency set point omega 0. The set point for the voltage is V0, which is defined according to the design of this voltage controlled nonlinear current source, HVOC. So by designing the way this function works, its limits, it's possible to define the voltage set point V0. The output from the VOC converter is given by the minus KV epsilon times IL. IL is the current flowing through the virtual inductor. The virtual inductor of the virtual, I say virtual inductor because it's an inductor that is present in the virtual oscillator control. That's why I call it virtual inductor. I1 implements this other controlled part, which is used to interact with the electrical system. So the controller has the power port to represent the current I1 and the voltage minus KV epsilon IL, which is used to modulate the converter. The modeling of the van der Pol oscillator is essential to understand the basis, the VOC. From the Kirchhoff voltage and current laws, from this circuit, it's possible to obtain 1. Then you can normalize in time, you can define a time basis, and from 1 you can obtain 2. 2 is a relatively well-known equation called the Leonard equation. The Leonard equation is widely used when you want to explore, when you analyze oscillators. And depending on the properties of the function f, it's possible to ensure a limit cycle oscillation. It oscillates, but in a stable manner. In this particular case, when f is defined in such a way that the derivative of the function h with h equal 3, then you get 4. So 4 actually models the van der Pol oscillator. So the idea here is to implement the equation 4, basically. Of course, we need to rewrite 4 in another form that is better, that's more readily to be implemented. But the equation 4 is it models the van der Pol oscillator. Now let's examine an example that illustrates the limit cycle oscillation behavior of the van der Pol oscillators. In the case where we define sigma, omega 0, and alpha equal 1, with initial condition equal 0.5 for the voltage VOC, then the van der Pol oscillator results 1. It was solved numerically. In this case, the portrait on the right shows that as the variable epsilon decreases towards 0, the trajectories becomes more and more sinusoidal. Now, in terms of application, okay, previously, this figure was presented without these inner loops. But in terms of application, we usually want to assign a given property, given nature to the line. In this case, we want to assign an inductive nature to the line. We are following the same developed for the droop controller with 2 integrators, and the virtual synchronous generators with the feedback of directive power at the gap and at the POC. We follow the same ways, the same analysis in terms of inner loops. So the inner controller is the same, and the virtual inductor is the same. The design is the same. So the system comprises the voltage source converter plus inner loops can be modeled. It's equivalent to this inductive circuit where there is a voltage controlled voltage source CC by a virtual inductor L, which is connected to the POC, the point of coupling of the grid, injecting the current I2. So the current I2 is now the quantity, the electrical quantity that is used to interface the VOC with the electrical part of the system. The output continues to be minus QV epsilon times IL. Now we are representing the VOC for inductive grids, for inductive lines in terms of state space form. This representation facilitates the analysis, the design, and the implementation. So from this circuit, we can obtain 1. This can be easily obtained. If you define the state variables x and y according to, and the omega 0, the coefficient beta, and the constant epsilon, then from 1, we will obtain 3. Okay, so 3 is the form that we're going to use it to implement the VOC. To implement the VOC, we can use 3. If we choose to model the converter using the state minus x is minus QV epsilon IL. Here, this variable. Okay, so we are using this output to modulate the converter. In this case, the input to the converter is minus QV epsilon times IL. in this case, okay, if you represent the VOC in polar coordinates, and after some manipulations, better details can be found here in the paper of Johnson et al., published in 2016. It's possible from this analysis to obtain 1. So from 1, we see that the reactive power, the average value of the reactive power, drives the dynamics of the voltage, while the average value of the active power drives the behavior of the angle, theta. So we have here the relation that is found when you have a controller for a grid-connected converter in an inductive line. So in this case, we made our VOC compatible with inductive lines. In this paper, for instance, if it was choosing another, it was made another choosing. It was defined that the converter was being modulated by the output Y. In this case, 1 had the opposite. The input to the voltage was P, the active power, while the input to the angle was reactive power, which characterizes a resistive grid. So depending on the choice you made, you can make the VOC compatible with grids or compatible with resistive grids. Here we are focused on inductive lines. So that's why we choose the modulating signal equal to -X. Okay, we now go through the dispatchable VOC oscillator control. We are not going to obtain results for the VOC because we have a dispatchable oscillator. The dispatchable VOC oscillator control that we're going to focus on from now, is given in the right. We can contrast, can put side by side the VOC oscillator control we have just seen with the dispatchable VOC oscillator we are going to cover from now. Here there are inner loops here in the right also. It was not represented, but when implemented, they have also inner loops implemented. So we have inner loops and virtual inductor. But what I want to call for attention for is that the fact we have the virtual inductor, the VOC oscillator control, which is implemented by a Van der Pol oscillator. And here we have another structure. It's still an oscillator, but it has some differences. First, it's designed to it's used to modulate a single-phase system. Okay, for a single-phase system, but we see here that when you want to use it for a three-phase system, it would be very straightforward because we have a beta component, which is in quadrature to the alpha component. So you have an alpha component, a beta component, and you should use both of them in a three-phase systems. But here we're focusing on single-phase systems, so using only the alpha component. The detailed block diagram for the implementation of the VOC is shown in this slide. So equation 1 details the structure of the VOC. The first term, okay, let's have in mind what the main objectives that we have when we want to design a controller for a grid-connected converter that must be able to operate in island mode. What do you need? We need set points for frequency, for voltage, and the ability to regulate the powers. So it must be backed. If you consider 1, we see that the first term on the right-hand side establishes the set points for the frequency. The last term on the right-hand side is the error. We can see this as an error of voltage, because V0 is the set point for the voltage, and V of beta is the magnitude of the voltage synthesized by the dispatchable VOC oscillator controller. The terms of power regulation the power regulation is in charge of the second term on the right-hand side. But if you look at this term at a glance, at a first glance, you cannot see, you cannot recognize how this regulation works. So, in order to have a better feeling about the regulation capacity of the VOC, let's rewrite the second term on the right-hand side of equation 1 according to equation 2. Okay, so we define the delta P and delta Q, which are some kind of error, of active power error and reactive power error. So it's possible to obtain 2. Okay, so the second term on the right-hand side is equal to this term here. So if you replace this expression into 1, it's possible to obtain this nice form. I'll allow you to call attention of all of you to this format, to this form. This is a nice form, and here it uncovers the droop behavior of the VOC. From the first term on the right-hand side, when you have a matrix, as all of you know, probably know, are aware, when you have a x dot equal a matrix times x, and this matrix is still symmetric, the elements defines the frequency of the system. So we see this element omega 0 plus eta divided by V0 squared times active power error. This term is the frequencies, the actual frequency of the oscillator. So we see here, we can recognize it here, the frequency droop equation, where the gain eta divided by V0 squared is the frequency droop coefficient. Okay, so if we can define M as the desired frequency droop coefficient in steady state. V0 is known, is the set point. So we can calculate eta, and eta is one of the 2 coefficients of the VOC. So we find one of the coefficients. Okay, now let's focus on this other equation, which is the input that drives the dynamics of V alpha, V beta. Here, what do we have here? We have something that resembles the error between the reactive power, the error of reactive power, and here we can express, we have the error of voltage. In the state, we expect that when this droop behavior goes to 0, which means that this term, we have this is the base of the droop behavior. The droop equation goes to 0. Okay? In this case, we have an autonomous system. We recognize here a droop coefficient associated with the voltage. So we have the voltage droop equal to 1 divided by alpha V0. So give desired voltage droop, we can design alpha, because V0 is known. The VOC in its original formulation achieved its objectives without measuring powers. Okay, so this is the same feature as the VOC. So the VOC also, the VOC and in VOC you are focusing on now, none of them they can share the power without the need of measuring the power. It's only necessary to measure the currents flowing out from the converter. But here we need to, we propose a modification. This modification is under study and we are working on it, and we plan to make some work in the future, in the near future. Basically, after some simulations, we verified that the VOC behaved better after a short circuit when, let's go back here, when we replace V alpha beta, so V alpha beta is in these droop equations is no longer the voltage synthesized by the VOC, but the voltage at the POC. So we want to regulate the voltage. We measure the voltage at the POC. So this is a slight difference between the original proposal of the DVOC and the DVOC we are using here, and which will be compared with the other primary controllers. So we call it improved DVOC. The structure is the same. We have inner loops. We have a virtual inductor. This system can be rewritten and redrawn according to this circuit, where we have a voltage controller voltage source V alpha, followed by the virtual inductor L, which injects we have the current I2 injected in the PLC, and the voltage V alpha is synthesized by the controller, the VOC. The microgrid, as an example, we bring two DERs, two equal DERs in terms of not only in terms of electrical quantities, but also in terms of design parameters. So they are both designed for the 10% of voltage drop and 3% of frequency drop. Then, using the previous equations, the given equations, it was possible to design the DVOC using alpha equal 1.62 and eta equal 55.22. Some results are obtained. Here, we have the black start of the DER1. The behavior of the DER2 is the same, so I didn't show you. I'm not presenting here. This is only for the DER1. So it presents a fast response. You can see that if you zoom the area around 1, here, we see that the transient response is very fast. However, the fastness of response was not designed. We can design the transient response, but it was not designed because we designed the DVOC in terms of the desired truth, not in terms of transient response. Okay? Because we want to compare with the others. The detailed waveform in 2, so we zoom at the waveform here and present it here, reveals the recovery of the DVOC back to the normal operation after a short circuit. We see here that there is some problems here. The short circuit occurs, the short circuit lasts only this time. At this point, the short circuit is cleared. It takes some time until the DVOC recovers at this point. So it recovers its normal operation at this, as detailed here. This is a problem. We figure out that with this choice of parameters implementing the original proposal, the DVOC didn't recover its normal operation. So we are still working toward and try to solve this problem. This slide illustrates the transient response due to a step change in the active in grid connected mode. So the grid is kept at its nominal values in terms of frequency, in terms of voltage. The set point for the reactive power is 0, and we give a step change of the active power from -1 PO to +1 PO. The change, we see that the system behaves very well. It injects an active. We can say that it behaves very well in terms of active power injection. But the reactive powers has some error. Reactive powers have some error mainly because there is a change on the voltage. This responds to error, the reactive power. Now another grid connected test. Here, the active power is maintained at 0. The grid voltage and frequency are at their nominal values, and this Q0, the set point for the reactive power, is changing from -1 to +1. A similar behavior is obtained. I can say that it's a good performance in terms of regulation. It does not track it because there is no secondary controller. We are only analyzing the primary controller. Okay, so there is no fine adjustment of the set point. It should be, you can say that it could be easily track it if you implement a secondary controller, but this is not the case. We see here a short coupling between active and reactive powers, but this coupling vanishes very fast because the VOC is very fast. Another grid connected test, we have the frequency grid drop from 60 Hertz to 57 Hertz abruptly. This causes the active power to increase. It's nominal value. The reactive power decreases a bit, the voltage, so there's a variation of the voltage, a variation of the reactive power, this is expected. And now the voltage decreases from, I'm sorry, this is from 220, not 200. So it decreases from 220 from 198 volts. This would correspond to an increase of reactive power of +1 Q, and we can see that it behaves not so good, but it's still possible. There are some errors here, and this error is mainly caused by this fact. We can see that the voltage in green at the point of common coupling changes. And if you're thinking about the implementation of the VOC, the voltage at the POC is an entry to the VOC. So as the voltage at the point of common the coupling changes, it's reasonable to assume that the VOC suffers a bit. So this explains the error, the steady state error of the reactive power in this case, because the voltage at the grid changes a lot. Now I bring the C code, the discrete time code that's used to implement the dispatchable Pol Oscillator control. Here we have the active powers calculated. They are used here at this point as entries of the VOC. Active power here, reactive power here. Here we obtain the absolute value of the voltage at the POC. Some matrices are defined, and finally we obtain the V alpha and V beta, the two components of the VOC. This is of course the discrete time implementation. Well, to summarize, let's summarize it. Let's make the summary for the VOC and for the VOC, the dispatchable Pol Oscillator. Well, in its original formulation, the VOC is not dispatchable. It has also some distortions on the output waveform to the converter. And this problem does not exist in the VOC. The VOC and the VOC, they exhibit a programmable droop behavior in steady state. Both of them can share power very well without the need of measuring active and reactive powers. Although, due to our modification, it was necessary to measure these powers. But in its original formulation, it was not necessary. So we are here to recognize that in the original formulation, there is no need of any power measurement. You only need to measure the output currents. The VOC and the VOC can be operated in resistive or inductive grids. We can tend to operate in both types of grids. The VOC, the Pol Oscillator control, the first controller presented, is mainly switchable for single-phase systems, while the VOC can be easily implemented in both single-phase or three-phase systems. Now we have the test-driven results, and I give the floor to Professor Humberto Pinheiro, who will continue the presentation. Thank you for all of you.